Sergey, thanks for joining us. And
Hello.
hope,
Can you hear me all right?
yeah, I can clearly see your slides and you also. So
Great.
that's fine. We let us wait for another 5 minutes for other participants to join, and then we will formally start. Okay.
Sounds good. And just to confirm, this is I've scheduled this for about an hour with questions.
Yeah, that's fantastic.
Okay,
Perfect.
great.
Okay, so Winter School team, shall we start now? Hello.
Yes, sir. So, yeah, we can start, sir.
Okay, so you can start the recording. Okay,
Okay.
so good morning, everyone, and once again, good afternoon, Levine, according to your time. Uh, Thank you very much for joining us to deliver this lecture over a short notice. Although it's a bit out of our schedule, but still, I believe many of the participants would be joining and would be very benefited by your lecture. Let me briefly introduce today's speaker, after which we will hand it over to him. Dr. Sergey Levine he earned both his BS and MS degrees in computer science from Stanford University in 2009, followed by a PhD in computer science under Vladlen Koltun from the same institution in 2014. He subsequently joined the faculty of the Department of Electrical Engineering and Computer Science at UC Berkeley in the fall of 2016. Sergey's research primarily revolves around machine learning for decision making and control, particularly focusing on deep learning and reinforcement learning algorithms. His seminal work finds applications in various domains, including the autonomous robots and vehicles. Among his research endeavors are the development of algorithms for end-to-end training of deep neural network policies, amalgamating perception and control, scalable algorithms for inverse reinforcement learning and deep reinforcement learning algorithms. He has made a significant contribution to the field, publishing in top tier and prestigious venues, including ICML and NeurIPS. And of course, although numbers do not say the last word, but he has an incredible Google Scholar H index of 158 at a very early age. So with this brief introduction, let me hand over the stage to Dr. Sergey Levine for this remarkable talk. Thank you, Sergey. The stage is now all yours.
Thank you, and I appreciate the kind introduction. So today I'm going to talk about reinforcement learning with large data sets. And while this is really a talk about reinforcement learning and control, it actually ties into generative AI and related topics quite a bit. But to start off, let's start with a little thought exercise. Let's think about a situation where we have to prepare a robot that's going to go and explore another planet. So this robot needs to be ready to handle whatever physical phenomena it encounters, but it also needs to deal with the unanticipated because we don't know exactly what it's going to find there. So besides being preloaded with a range of behaviors that allow it to handle diverse situations, it also needs to be able to adapt and handle the unexpected. It's a little bit like what you might imagine a person has to do if they are stranded on a deserted island and they have to fend for themselves. So they're going to bring to bear their past experience to robustly navigate whatever situation they're in, but they'll also have to be resourceful and adaptive. And that's in fact one of the hallmarks of intelligence, that resourcefulness and adaptability. So if we want to equip our interplanetary robot to go and explore another planet, what are the state-of-the-art AI techniques that we could draw on that might help make that possible? Well, what are some of the recent big advances? There's data-driven generative AI, and then there's reinforcement learning. These are two things that over the past decade or so have garnered a lot of attention. They seem like, you know, the really state-of-the-art advances. What can these two categories of techniques give us that would help us prepare our robot for the unknown that it might encounter? Well, what about the data-driven generative stuff? How does it actually work? We've seen that data-driven techniques can allow us to obtain very powerful image generation models that can generate pictures based on text prompts, chatbots, large language models, very capable machine learning systems. But at some fundamental level, what these techniques are all doing is modeling the data distribution. A language model does literally that. A language model literally predicts future tokens in the data distribution. Image generation models might model a conditional distribution over images given prompts. And at some very fundamental way, this is an extremely advanced version of what we learn about in elementary statistics about fitting distributions to data sets. And then, of course, it makes sense to ask, well, what is the distribution that is being fitted? If you're training, for example, an image recognition model, something like CLIP, well, the data distribution is the distribution of images that people post on the web. If you're training a language model, the data distribution is the distribution of text that people type and place on the internet. So at some very fundamental level, what these models are really doing is emulating the distribution of data produced by humans and placed on the web. What does reinforcement learning do? Well, reinforcement learning is seemingly a very different type of thing. Reinforcement learning is about having an agent interact with the environment, improve its behavior through that interaction with respect to some objective, and then repeat the interaction again many times. And we've seen reinforcement learning succeed also in a pretty big way in domains ranging from video games to beating the world champion at the game of Go to robotic control. But these are very different things at some level. And I'm going to argue that they actually have very complementary strengths and weaknesses for our interplanetary exploration robot. So one of the really exciting things about reinforcement learning is how it can lead to emergent behaviors. One of the most remarkable moments in the AlphaGo Lee Sedol match was the so-called move 37, when the AlphaGo system chose a very good move that ended up winning at the game, but it was a move that the human commentators, the human experts at the game really didn't expect. It was a move that surprised everyone. So the data-driven generative AI methods are very impressive because they produce the kind of content that humans might produce. They draw pictures like the ones that humans might draw. The reinforcement learning methods are impressive for exactly the opposite reason, because they can come up with solutions that no person had thought of. And that's a very big distinction. And for our Mars exploration rover, perhaps it'll need both of those things. It will need to handle problems as proficiently as a human, but it will also need to come up with novel solutions that no one has thought of. Now, of course, reinforcement learning by itself in its most classical form is not sufficient to solve everything either, because the big successes of reinforcement learning have been in domains that are relatively narrow. So the game of Go is a complex game. It has a lot of depth, but it doesn't have a lot of breadth in the sense that there are not a lot of unexpected phenomena that come up in the game itself. The AlphaGo system never had to worry about a person spilling coffee on the Go board and having to deal with the result. It lives in this constrained environment of the game of Go. And that constrained environment is much more narrow than our environment, which has physics, objects, diverse environments, other agents. All these complex phenomena place a much higher demand on generalization. And for that reason, standard reinforcement learning methods by themselves have generally not been very effective at handling truly complex open world settings. So there's a big gulf, and it's really the gulf of generalization. To bridge generalization, we need very large data sets. But if we use reinforcement learning with very large data sets in this iterative online process where each time a little bit of data is, where each time a large amount of data is collected and that large amount of data is used to update the model for many, many iterations, that means you're collecting ImageNet-sized data sets every iteration, and it's very hard to make that scalable. So where does that leave us? The spoiler for where that leaves us is actually in the chat. Someone kindly already spoiled the outcome. Thank you. It is in fact where I'm going. But to set this up a little bit better, where that leaves us is this, that the data-driven AI techniques learn about the world from data, but they don't try to do better than the data. A really good language model emulates the behavior of a person, but it doesn't attempt to do something truly superhuman. A reinforcement learning system optimizes a goal with emergent behavior. It can reach superhuman performance, but without the benefit of learning from real-world data, it's constrained to solve problems in a more constrained and narrow setting. So games are really an ideal setting for these types of RL techniques because they don't require that broad open-world generalization. So the data-driven methods are all about using data. Reinforcement learning is all about optimization. And of course, as you might expect, what I'm going to argue is that we really need to combine both of those. That data without optimization doesn't allow us to solve new problems in new ways. And optimization without data is hard to apply to the real world outside of narrow simulations. So can we learn to make decisions with data? Can we really get the best of both large data sets and emergent behavior and optimization? So the framework that I think gives us a really powerful way to get at this is offline reinforcement learning. Online RL methods have this iterative procedure where they interact with the world, improve the behavior, and then keep getting better. Offline RL methods, however, take a static data set that was already collected, basically past experiences that our Mars exploration rover can draw on, use that past experience to recover the best behavior they can, kind of squeeze out the most optimal behavior from that data, and then they're deployed, and after deployment, they can be fine-tuned further with additional online reinforcement learning. So this is maybe a little bit abstract, but we can tie this back to our interplanetary exploration robot. Perhaps what this robot can do is it can start with a large data set, from experiences that it had here on Earth, much like a human astronaut might learn from training here on Earth, including experiences from other robots, maybe even experience from humans, maybe even experience from other situations that are not directly reflective of what it will find on the other planet, but give it a good basis to start from. Basically teach it something about intuitive physics, about cause and effect, about the kinds of phenomena that can take place in the world. And that goes into offline reinforcement learning to prepare the best policy you can before you deploy the system. Just like a human astronaut might train and figure out the best skills before they're sent on their mission. But then once it's sent off, it's put on this rocket and sent to Mars. Now it can do additional online improvement to adapt intelligently to whatever unfamiliar situation that might happen, so that when something unexpected does happen, it can actually come up with a novel solution to this unexpected problem. And then we can get the best of both worlds. We can get that generalization from priming it with these large data sets and have the ability for it to squeeze out the best behavior from that data set and then further adapt with additional learning. So in this talk, the key topic I'm going to focus on is what can we accomplish if we combine data and optimization. Unfortunately, I was not able to send an interplanetary robot to Mars to explore another planet. My results are much more modest than that, but hopefully what I can tell you about will give you a little bit of a hint for where some of these technologies could be going in the future. So I'm going to start with a discussion of offline RL fundamentals to tell you a little bit about the kinds of algorithmic ideas that exist in this space. Then I'll talk about applications to robotic foundation models, basically large robotic models that can train robots for a variety of tasks. And these will make use of offline RL. They'll also make use of other ideas. Then I'll talk about reinforcement learning with generative models. And then I'll talk about offline RL and language models and for conversational AI. So this will cover a few different applications of these general principles. But let's start with the algorithmic fundamentals. So what do we expect an offline RL method to really do? Well, one piece of intuition, which is reasonable, but maybe doesn't quite tell the full story, is that maybe it's a little bit like imitation learning. Maybe if you have some data that performs some task, like moving from the green circle to the orange circle, maybe it's a little bit like copying that data to find the corresponding policy. I think that's not the best intuition. I think that offline RL does a lot more than that, although even in this setting, it is provably a good solution. But a better intuition is that offline RL is about taking very diverse data and using it to figure out the best possible solution that is supported under that data for a new problem. So if you have very diverse data that performs many different things, can you recombine pieces of that data, basically use the data to figure out what you can do, and then from there figure out the optimal solution, figure out the options from the data, figure out the policy from optimization. The most obvious example of this is a kind of a stitching example. If you've seen in the data that you can go from A to B, and you've seen that you can go from B to C, you should be able to figure out that you could go from A to C, right? So you can figure out essentially a transitive property. But the key idea is that this can happen not just in one place, but everywhere all at once. For example, humans driving cars, and maybe each human driver is good in some places, but worse in others. If you can synthesize a policy that is as the best human in every situation, that can be significantly better overall than any one human driver. So by pulling out the best pieces of the data everywhere and recombining them optimally, you can actually achieve much better solutions in principle than any single behavior you've seen in your data set. And that's a lot more powerful than simply copying the data. Now, I won't go into a lot of detail about the actual algorithms. This is, I want this talk to be a little bit more high level about the principles, but I do want to give a quick primer to some of the fundamentals in offline RL. So in reinforcement learning, we have an agent that chooses actions A, and the world responds with states S and rewards R. The actions are distributed according to a policy, pi of A given S. And the objective in reinforcement learning is to maximize the sum of expected rewards. So the total reward the agent will achieve over all of the time steps of the interaction. A very useful object for doing this is what's called the Q function. The Q function tells you if you start in a particular state ST and then take a particular action AT, what is the total reward that you will accumulate from there if you follow the policy pi? So it's the total reward you'll get if you run the policy after state S and action A. And it turns out that you can always recover a new policy that is as good or better than your previous one if you're simply greedy with respect to the Q function. Essentially, if you take the action such that after that action you get the highest reward, that'll be a better policy than the one you started with, unless you already have the optimal policy to begin with. And that's the basis for something called policy iteration. You can also short circuit this process and immediately train for a Q function such that the Q value is equal to R plus the max of the next Q. And that's basically substituting that argmax into the equation for the Q function, and that also recovers the optimal Q function. And that's the basis for Q learning. So a very classic way to train optimal Q functions is to minimize the difference between the left-hand side and the right-hand side of this equation at all the states, and that's basically the classic Q learning algorithm. Now, the interesting thing about this approach is that the Q-learning framework doesn't actually assume that your data came from any particular policy. It is what's called an off-policy method. So the foundations of most current offline RL methods are based on this fundamental equation. Minimize the difference between the left-hand side and right-hand side of what is called the Bellman optimality equation, this equation for Q star. So on the surface, it might seem that this is very good, that we can simply use this approach, get an optimal Q function, take the argmax to get the policy, and then we're finished. But it turns out that it's not so simple. The issue is that if you're training from static data and you're not collecting any additional data from the latest policy as you go, there's a really big problem. And most current offline RL methods are basically about finding some solution to this big problem. So to see the problem, let's rewrite the Bellman optimality equation in a slightly different form. Instead of taking the max over the next action, we'll take an expected value under some distribution pi nu, where pi nu is defined as the argmax. So pi nu basically is that greedy policy from before. So we didn't actually change the equation, we just wrote it in a different way. Instead of the max, it's the expected value for a distribution that puts all the probability mass on the argmax. And now we can see that this equation makes sense if the expected value of Q under pi nu is correct. Now Q is a trained neural network. So if you want to know whether a trained neural network will be accurate in expectation under some distribution, the question to ask is, how was it trained? What distribution was it trained under? And of course, it was trained under the distribution that generated the data set. So it was trained to regress onto the right-hand side, which I've labeled as Y here, to minimize Q minus Y, in expectation under what is called the behavior policy, which is whatever behavior generated our data. And now, of course, we have a problem because pi beta, the distribution of the data set, is not the same as pi nu. So we expect good accuracy when they're the same, when you're testing under the same distribution as the one under which you're training, but of course we're not. The whole point is that we want pi nu to be better than pi beta, to have a higher Q value. And that's really bad. It's really bad because pi nu is not only different, not only do we have the distributional shift, it's actually chosen in an adversarial way. It's chosen to maximize the Q values. So if you choose the new policy to maximize the learned Q values, and the Q values are trained on a static data set, you will fool the Q function neural network, much like adversarial examples fool image classifiers. And in fact, this is exactly what we see if we run experiments. If we use standard naive Q learning style methods, they will estimate that they will get very, very high rewards. So the right-hand side shows the estimated plot. The y-axis is a log scale. So they're estimating something like 10 to the 7th power or 10 to the 20th power, but they receive average rewards of minus 250 or so. So there's massive overestimation. The Q function thinks it will do much better because the policy is exploiting it by producing adversarial examples. So what can we do? Well, there are many different methods, but similar principles seem to be effective across a range of different offline RL techniques. So one of the ingredients is use value-based methods, so Q learning or Q function actor critic. But then somehow fix this distributional shift problem, which could be done in a number of ways. One way to fix it is with something called pessimism or conservatism, which basically means find the actions that have very high Q values and minimize their value. It's very much like adversarial training. Adversarial training finds adversarial examples and corrects them. Pessimistic or conservative Q learning methods find high Q value actions and correct them by minimizing their value, very much like adversarial training. Another possible solution is to constrain the policy, limit it from deviating too much from pi beta, because if the source of overestimation is distributional shift, if you can limit distributional shift, you will have less overestimation. And then there are also some more exotic solutions. For example, we can even derive modified types of Q learning methods that avoid maximization altogether and use some implicit maximization techniques. And that's the basic approach behind something like IQL, implicit Q learning. In regard to the question on chat, yes, CQL means conservative Q learning. There are a variety of conservative methods. Conservative Q learning by Aviral Kumar is probably one of the best known methods in this category. So it's very complicated as to which method is better in which situation. I think the truth is that we as a community haven't fully figured out exactly which methods are best. But methods like IQL or CQL provide a very reasonable starting point if you want to get started on this topic. So I'll go into a little bit more detail about conservative Q-learning just because I want to use it as an example. I'm not trying to say this is the best method you could use, but it's a fairly simple method to understand, so I think I can probably summarize it pretty easily in a single slide. So conservative Q-learning basically tries to address this overestimation problem, and the way it does it is very similar to adversarial training. So at a very high level, you can imagine that there's some function you're trying to learn. That function you can fit in a pretty reasonable way. But if you try to maximize your learned function, shown in blue, you might find exactly the point where it overestimates the most. So the idea in conservative Q-learning is to find those points where you have the largest value and minimize their value. And this is done in a fairly simple way. We take the original Q-learning objective that's shown on the second line, minimize the difference between the left-hand side and right-hand side of that Bellman equation, and we add to it a kind of adversarial regularizer. So this adversarial regularizer shown on the first line finds a distribution mu, which maximizes the Q values, and it actually minimizes the Q values under that distribution. Much like adversarial training would find points that assign the wrong label and would correct those points. So very simple, just find the high Q value actions and minimize their Q value. The actual method is a little bit more involved than that, and it turns out that there are a few tricks to make this objective very tractable, but this is basically the high-level idea. So there's the regular objective and a term to push down the high Q values. And in fact, this method can be shown to have very appealing theoretical properties. For example, with a large enough coefficient on the regularizer, you can actually prove that it will not overestimate. Okay, let's look at an example application of conservative Q-learning to a kind of a large-scale pre-training and then fine-tuning scenario. It's not going to be quite our Mars rover, but it will have this property of pre-training on diverse tasks and then fine-tuning, and we'll do that with Atari games. So this is an experiment that Aviral Kumar, together with Rishabh Agarwal and George Tucker, conducted in a paper called Offline Q-learning on diverse multitask data, both scales and generalizes. What they did is they took a data set with 40 different Atari games, and they trained a single model with conservative Q-learning on all 40 games. Now, the model has actually a different head for every game, but the rest of the network is entirely shared across the games. And just from offline training, this method works quite well. The plots on the right show the average offline RL performance when tested on the 40 training games. So this is not generalization of new games. These are the training games. And it's comparing decision transformer with either 200 or 40 million parameters, behavioral cloning, and two variants of CQL, one with a small network, that's the MT Impala DQN, and a much larger network, which is the real method, scaled QL, and that one has 80 million parameters, so actually less than the largest decision transformer. And you can see that especially with a suboptimal data, it actually does quite well. The dotted line shows the average performance in the data set, and you can see that the offline RL method with a pink bar is much better even than the average in the data set, especially when the data set is highly suboptimal. In fact, it's a 2.5x improvement over the prior result. But the more interesting thing for me is that this can then serve as a pre-trained model, a kind of Atari foundation model, if you will, that you can then fine-tune to other games. So for example, you can fine-tune it with offline RL with a little bit of data from a new game, Alien, Miss Pac-Man, Pong, etc. These are not one of those 40 games. And you can actually get very good results on the downstream game. The other methods, some of them do better, some of them do worse on the different games, but across the board, the pink bar scaled Q-learning is the best performing one. So that one is the most reliable. You can also fine-tune with online RL. Here we're fine-tuning with online RL to variants of the training game. So these games have different modes, and we picked a mode that is different from the training mode. That's just a mode switch in the Atari emulator. And here again, we can see that scaled QL, the pink bar, actually fine-tunes more effectively, even with online experience. Now, these techniques have been used across a range of applications. Some of them I'll talk about today, including robotics, dialogue systems, Atari games, as well as other more commercially relevant applications. So other people have applied conservative Q-learning to optimizing click-through rates for mobile notifications, basically push notifications that users are more likely to click on, and optimize that using offline RL, using data from past user interactions. Digital management systems for optimizing conversion. This is for digital marketing. There, people have also seen that offline RL with conservative Q-learning can actually lead to significant improvement. So these are like pretty interesting application domains where it's easy to get data, but it's comparatively very risky to just do straight up online RL from scratch. But the applications I want to talk about next maybe will bring us a little closer to these larger scale things that we're thinking about, like these interplanetary exploration robots. So what I'll talk about next is an application of some of these ideas to develop robotic foundation models. And I'll say off the bat that a lot of what goes into developing robotic foundation models is not just algorithms. A lot of it has to do with data and other components, which are largely separate from the RL part, but I think they're also very interesting to talk about. So if you want to build a general robotic foundation model, a model that can be used by many different kinds of robots, we need to get a few ingredients right. We need to get large-scale robot data sets. We need to get these self-supervised robotic learning algorithms, which we can derive from offline RL, and we need flexible and general models. And if we can have all of those things, then we can perhaps build a large general-purpose robotic foundation model, which could be used maybe even for our future interplanetary exploration robot. Although for now, our goals will be a little bit more modest. So one of the areas where we started working on this topic a while back, and this was in work led by my student Dhruv Shah, is for robotic navigation. Still on this planet, however, not on other planets. So what we did to get started is we collected a large data set consisting of diverse behaviors from many different kinds of robots. These are all ground robots, navigating robots, but they range in size from small RC cars to full-scale ATVs. There were 8 different data sets with 6 different robots. And what we did originally is we actually trained a much simpler model. This model doesn't actually use the kind of Q-learning-based methods from before. It actually uses a very simple goal condition policy. And this goal condition policy takes in the current observation and a photograph of a goal image that the robot should navigate to, and it predicts the optimal action to take from there using the data set. And it receives a little context, a little history context that it can use to figure out what kind of robot it's controlling. And if we train this model, it turns out that because the dataset has a variety of robotic platforms, the resulting model can actually generalize in zero shot to control even entirely new robots. For example, I can fly a drone through hallways, even though it was never trained on drones before. Now, the drone is pretending to be a vehicle. It's flying at a fixed altitude. It's not controlling up and down. It's only controlling sideways motion. But nonetheless, it's zero shot generalization. So this suggests that we can get pretty broad generalization to new situations. More recently, we've extended this with large transformer-based models. So we can design a transformer model that actually reads in the context and the goal, and then it predicts the actions and the temporal distance, which you can think of as basically a value. So it's a kind of an actor critic style approach. And that can also control diverse robots. People have actually used it for a variety of applications in other labs as well. One of the nice things you can do about it is you can actually fine-tune it to new tasks. So you can take the pre-trained model, substitute out the encoder, the goal encoder, and replace it with an encoder for a different control modality, like, for example, turn-by-turn directions. And you can actually get it to control simulated vehicles in Carla with just a little bit of fine-tuning. So that's very promising. That suggests that it has many of the properties we would associate with a foundation model. It can be fine-tuned to downstream tasks. It can generalize in zero shot. And it has actually been used by other people around the world for things like flying drones, navigating through forests. So people have used this in a variety of places from Estonia and Finland to Princeton. But one of the things that I'm particularly excited about that we can do with these kinds of models is we can actually implement this offline RL pre-training followed by online fine-tuning cycle that I described at the beginning of the talk. So one project I want to tell you about is called FasterLab, where we use this multi-robot pre-training data, extended it to use offline RL, pre-training with IQL, and then performed online fine-tuning to rapidly adapt this model to drive at high speed around a building. So at the beginning, it doesn't, as you saw in that video on the right, it doesn't navigate the building very well. It's a new robot, it's a new environment, it's being asked to also control the speed. So it roughly knows the idea, it knows it needs to follow hallways, but it makes many collisions. But after a little bit of training, it very quickly starts doing better. So after 15 minutes, it can mostly make its way around the hallway, although it's not very fast and it still collides. But after a bit more training, after about 25 minutes, it can actually race around the building quite proficiently. And in fact, from the first-person perspective, the speed at which it goes through the building is comparable to what an expert human driver would get if they use the same first-person perspective. The human can do a bit better if they use a third-person perspective, but for first-person, it's about the same. I think this is actually really interesting because 25 minutes to train a policy with online RL from pixels is very, very fast. So the offline pre-training is giving us a lot. We can use the same approach for learning to drive outdoors. So here the robot needs to go through checkpoints. The checkpoints are located on the grass. This is the initial policy before the online phase. But after the online phase, it actually learned that it has to go on the grass to reach the checkpoints, but in between the checkpoints, it can cut through the paved path, and on the paved path, it can go quite a bit faster. So there's interesting emergent behavior, not quite Move 37, but something promising, and the ability to actually adapt in this environment in under an hour, between 15 and 30 minutes, using this offline RL pre-trained model. So here's the first-person perspective for outdoor driving, and you can see this is not an easy task. It's very bumpy. The camera shakes a lot, so it's fairly tricky for the robot to learn this behavior. Okay, so that was navigation. Navigation is maybe not the most complex task. It has a fairly small action space. What about manipulation? Can we do all this for robotic manipulation tasks? Now, for that, it's very important to get the right data because manipulation involves interacting with a very diverse, broad set of objects, a huge range of situations. One of the things we did to facilitate this is we collected a very large data set. We call it Bridge Data V2. We actually had V1, which was quite a bit smaller. V2 has over 60,000 trajectories of robotic manipulation skills, hundreds of objects, and full language annotations for all the trajectories in 24 different environments. Having many different environments is important because that means that models trained on this data will also run in other labs and other locations. And the data is collected with a low-cost robot called a Widow X robot. It's comparatively less expensive than industrial arms, which makes it more accessible. Now, just this data set alone actually already enables relatively simple methods to learn fairly complex skills. The videos that you're seeing show a goal condition policy trained very much in the same way as the navigation foundation models from before. And just because the data set covers so many different tasks, we can actually get policies with fairly naive methods without really doing anything novel that can perform this wide range of behaviors. So all of these goal-reaching behaviors are performed with the same policy: folding cloth, manipulating furniture, drawers in this case, moving objects, sweeping clutter. We can also train language condition policies in much the same way because the data set is annotated with language. And again, the same policy can perform all of these tasks. And what's interesting here is actually the fact that the methods are not novel. The methods are very simple. And it's just the high quality data already provides a very capable base level policy. But now we can start adding RL, and we can add RL in some pretty interesting ways. One of the things we can do is we can use offline RL pre-training with online RL fine-tuning and include large amounts of video data. So one of the things we developed in a paper called VPTR, video pre-training for robots, is a method that can first run RL on videos, in this case from Ego4D, then use that model to further train with offline RL on bridge data, and then further fine-tune on a single downstream task to get the best performance. So the method that we use with the video data is something called ICVF. It's a variant of the IQL algorithm that we've modified to train without supervision, without rewards, and also without actions. So you can roughly think of it as learning to reach diverse goals. It's actually a latent representation of goals called intentions, and the actions actually end up being factored out by using a modified IQL method. I won't have time to go into the technique in detail, but you can find out more about it in the paper. And then the second stage is done with a variant of conservative Q-learning. And then the third stage fine-tunes to a particular downstream task in a new environment. So on the right here, you can see some of the tasks that we fine-tuned to in our experiments, and the table shows the results. Now, these are fairly difficult tasks, so the average performance of our method across a range of different tasks is about 50%, so there's still room for improvement. The interesting thing, however, is the right two columns. If we don't have any robot data, meaning you don't have phase 2, so you just have videos and the downstream task, the performance is 7 out of 48. If you don't have videos, it's actually 5 out of 48. So the videos actually help a little bit more than the diverse robot data. But if you have both, then you get a huge improvement. Then you actually get about half, 50% success rate on these fairly difficult and heterogeneous tasks. Now, one of the really exciting things that came about since this work came out is a project called RTX, which was led by folks from Google, as well as my postdoc, Carl Perch, which aimed to actually extend some of these ideas to not just have one diverse data set, but many diverse data sets across many different kinds of robots. And I think this really points the way towards how we might see robotic foundation models evolving in the future. So in RTX, a very large data set was assembled with contributions from 34 different research labs and 22 different types of robots. Bridge Data V2 was one of the data sets, but there were many others. There were 60 data sets total for a combined total of about 1 million episodes. And these data sets were very diverse. I have lots of statistics, but instead of showing the statistics, I figured that maybe it's best to just show some videos. And these are videos of the different robots in this data set. And you can see there's a lot of variability from the bridge data style kitchen robot to a robot that routes cables, a Franken robot that opens drawers, the stretch robot manipulating, in this case, trash containers. There's a lot of variability, a lot of different embodiments. And a single model can be trained on all of these embodiments and then tested by all the different research labs that contributed data. So in this case, this plot is showing an evaluation at 5 different research labs where the comparison is between what is called the RT1X model, which is a language condition policy that was trained on the combined data set. That's shown in the rainbow colored bar. And the best model that was previously developed by that lab, that's shown by the colored bar on the left. And then the gray bar shows the standard RT1 model trained in that environment. And you can see that on average, the cross-embodiment model, the one that was trained on all the different robots, is on average 50% better than whatever was the best model that was developed in that individual lab for that individual data set. And what that means is that combined data from many robots really helps. It helps by about 50% on average in terms of success rate. Now, these results do not use offline RL at this stage. They still use imitation learning, but it's a very natural next step to then combine these kinds of methods with the kind of offline RL that I showed before, for example, in the VPTR project. In fact, there's already work on scaling up offline RL techniques to large transformer-based models. One example of this is the Q-transformer project. In Q-transformer, the idea was to take a model similar in design to RT1, the same model that was used on the previous slide, but now train it with offline RL, although in this case it was on a more narrow data set. This actually predates the RTX project. And one of the things that's different about transformer-based models is that in the standard way of training them, they would output an autoregressive discretization of the action. So instead of a continuous action, they output action tokens, typically with one token per action dimension. It turns out that it's actually pretty straightforward to adapt this to offline RL because now you have actually a discrete action space just with different dimensions serving as time steps. So if before you had capital T time steps and dimensionality D, now you have T times D time steps with each dimension serving as a different time step for its own Bellman backup. And that can be used with a standard discrete action Q-learning algorithm, which can, of course, be extended to handle offline data with conservative Q-learning. And that was actually the approach taken in Q-transformer. These are the tasks that were tested. As I said, this doesn't yet use the multi-robot data. It only, in this case, it uses only data from a robot at Google. But there's a pretty large improvement. So here, the right comparison is between the rightmost column, which shows the imitation learning approach, and the leftmost column, which shows Q-transformer, which also integrates negative data, meaning data of failed episodes, which cannot be used for imitation learning. So the amount of successful episodes is the same, but Q-transformer also has failed episodes, and just the addition of those failed episodes allows Q-transformer to lift up the average success rate from 25% to 56%. So over a 2x improvement just from incorporating failed attempts. And that makes sense because offline RL can use those failed attempts, whereas imitation learning cannot. Okay, so what have we done in regard to robotic foundation models and what remains open? Well, robotic learning from multi-robot datasets seems to work and enables models that people around the world can use. So the same model checkpoint can be sent to many different labs and they can test it. Offline RL can enable more performant policies, and it can enable rapid online RL fine-tuning, as you saw in the driving examples. This seems to hold for both robotic navigation and manipulation. But the largest models still use imitation learning, and integrating all of the components is yet to be done. Scaling offline RL methods is a challenging proposition, but with techniques like Q-transformer, we're getting closer and closer to that. So perhaps once you put all these pieces together, we'll be even closer to a true robotic foundation model. So there's many advances that will get us there. So that's robotics, but I want to also talk about other areas where the combination of using large data sets and optimization can lead to really interesting results. So for the next portion of the talk, I'm going to talk about how RL can be combined with generative models for image generation and also enable interesting emergent behaviors. So just to remind you what I talked about in the introduction, data-driven AI is all about using data. Reinforcement learning is all about optimization. So far, we talked about how to make RL and control better by leveraging data. So robotics is basically a control problem, and we saw how we can make robotics work better by leveraging large data sets. But can we also make generative models better by leveraging RL? Can we go the other way? Can we include that optimization into areas that traditionally just rely on data? So why should we expect generative models like image generation models to benefit from reinforcement learning? Well, remember what I said before, that these image generation models are impressive because it looks like something that a person might draw. But the thing is, we don't just want pictures that people already drew. We want new pictures. We don't just want to make the pictures that already exist. Maybe we want a very novel picture. Perhaps we want to ask the system, what would it look like if a dolphin was riding a bicycle? That's a very unusual question. If you send this prompt to Stable Diffusion 1.4, this is the picture that you will get. Now, I do think that more recent diffusion models will do better. This is a fairly old model. Back when we did this research, Stable Diffusion 1.4 was what we could use with our compute. Probably newer models will do better, but it's still a very difficult prompt. Why is it difficult? Well, it's a little bit like Move 37. Basically, asking the model to draw a dolphin riding a bicycle requires a novel solution to a new problem. Dolphins don't ride bicycles, people don't draw dolphins riding bicycles, so it requires some kind of emergence. And this is where I would posit RL can be a big help. For the question about what to do when human experience is not directly available, I will actually address that question later on. So when I talk about language models in the last portion of the talk, I'll actually address an example that has exactly this property. So for the gentleman that asked this question, please hang on, and I'll answer that later. Okay, so we need optimization to get emergent behavior, like these kinds of very novel prompts. So how can we do that? Well, what we can do is we can set up an RL system that actually uses an image capturing model as a reward signal. So let's say that we have some prompt like a monkey washing dishes, which is a little bit unfamiliar. We're going to give that prompt to a diffusion model, and that diffusion model will make some attempt. And that attempt might not be very good. So it has some hint of what's going on, but if you look at this picture, you probably wouldn't say that it's a monkey washing dishes. And then we ask a VLM, like Lava, what is happening in this image? And the VLM will produce some answer. In this case, there's a monkey, so it'll say a monkey is, but maybe the monkey is not doing the right thing. So it'll produce something that's close, but a little bit off. And then we'll assign a reward based on BERT score, as far as how close we are to the prompt. So the visual language model basically provides a reward based on semantic content. And then the reward signal is then used to improve the diffusion model to get the semantic content to be closer to the prompt. Now, at first, this might seem a little circular because the VLM itself is trained on internet data, as is the diffusion model. So where does the benefit actually come from? Well, remember that the diffusion model is not trained to draw pictures that reflect prompts. It's trained to model the data distribution. When we train the model with RL in this way, we're actually telling it what the task is. The task is not just to produce the kind of images that are most likely to correlate with a prompt monkey washing dishes. The goal is to produce a picture that when someone looks at, they'll say, oh, that's a monkey washing dishes. It's actually a subtly different goal. We're teaching the model to solve the task rather than just copy the data. And the task is to produce the image that will be recognized as corresponding to the prompt. So let me show you an example of what this looks like. Or let me first tell you about the methodology, and then I'll show you the example. So the technical challenge is that diffusion models are not easy to optimize with RL. Diffusion models don't have closed form likelihoods. So because of that, classic RL methods that rely on computing the gradient of the log probabilities don't really work with diffusion. But what we can do, however, is we can leverage the fact that the diffusion process itself can be viewed as a temporal process. Much like an MDP is a temporal process, diffusion is a temporal process. And at every step of diffusion, there is a closed form log likelihood for that diffusion step. So the algorithm that we actually utilize in this work, called DDPO, denoising diffusion policy optimization, basically treats every step of diffusion as an MDP time step, and then uses policy gradient. So every step of diffusion has a well-defined grad log P, and then the reward is assigned at the end of the trajectory, and we use a method that is very similar actually to PPO, but at the level of these diffusion trajectories. And this actually works really well. You can optimize a variety of objectives from aesthetic quality to JPEG compressibility. You can even do something strange like make images that are hard to compress if you really want to. It works better than alternatives like reward-weighted regression, and generally seems like a pretty scalable and stable method. And I should mention at this point, there's some concurrent work called DPOK from Fun et al. That proposes a very similar method. So these works actually came out just a few days apart, proposing similar techniques. But now let's go through an example of this method in action. And I'll use this prompt a dolphin riding a bike to illustrate this. So as I showed before, here's the initial image that Stable Diffusion 1.4 will generate. And then if we evaluate the reward using Lava, we pass it to our RL method, and we improve it for a few iterations. This is the image we get. Now here you can see there's a bicycle and there's a dolphin, but it's not quite coming together just yet. A few more iterations, and we get this image. And after a few more iterations, you can see the image becomes a little bit cleaner. Now it's much more obvious that it's a dolphin, and this is the final image at convergence. Now, I should say this method is not actually optimizing for a single prompt. So it's actually optimizing for a distribution of different prompts, and I'm showing only the dolphin images. In reality, there's a huge range of prompts that in this case all have a theme, and the theme is animals performing tasks. So there's a distribution over animals, a distribution over tasks. Every iteration, you sample a batch of random combinations, and that's how the optimization proceeds. So to show you more of the examples, here are other animals doing other activities, and we can plot over time the BERT score for the different models. And one of the interesting things is that when we do this kind of analysis, we actually find that for some of the animals, the dolphin was one of the hardest ones, initial performance is extremely poor. But other animals are a little bit better. And because of the randomness of RL, some of the prompts become better, and they actually help lift up all the others. So there's a generalization effect going on. And you can see that in the end, all of these different prompts produce images that kind of plausibly resemble what they're supposed to be doing. And in fact, you can actually take the model after RL training, and you can test it on new prompts to look for generalization. And when you test it on new prompts, you can actually see that for something like a robot fishing in a lake, it actually produces a better image after RL training, even though it was not trained for a robot fishing in a lake. So it's generalizing from other examples. There's a really nice question in the chat, which is, why are the end images cartoony? So you'll notice here that towards the end of the optimization, fairly consistently, the images look more like children's book illustrations. We don't know why that's the case. We might guess that maybe it has something to do with animals doing activities is maybe more often found in children's books, but we really don't know. It's kind of an interesting phenomenon, and it'll be fun to explore further why that happens. Okay, in the last portion of today's talk, I'm going to talk about one last application, which is applying offline RL to large language models. And that's another kind of generative model. I think it's also an interesting data point to consider. So one of the things we could try to do with large language models is learn to better interact with humans. Let's say that you'd like, for example, to have a virtual tech support agent. Perhaps you can pull up a data set like the Ubuntu Dialog corpus, which has basically chat rooms where humans interact with each other on the topic of basically Ubuntu debugging. And you could imagine maybe you can train a language model, you can fine-tune it on this data set and get a better tech support agent. So you'd like to take this data set, put it into some kind of algorithm, and get out a language model that can help humans solve their tech support problems. The trouble with this is that just copying the humans doesn't lead to great performance, because the data doesn't actually have optimal tech support agents. The data just has people talking about random stuff. Sometimes they'll even say, like you can see in the example here, tasks that are, responses that are not very helpful. Like it says, oh, you can use PSOX and kill a process, and that's actually just a prank to get somebody to kill a process that they shouldn't, what they shouldn't do. So just copying the data isn't necessarily optimal, but the data has a lot of information about how humans respond to other humans. So in principle, you could analyze that data and get a better agent that leverages the patterns that it observed to help humans more optimally. Don't just copy the humans, but find out which responses actually get the best results. So can we leverage these patterns to do better than humans? Well, maybe we can do this with RL. One very well-known RL technique for language models is RLHF. Can we use RLHF? Well, RLHF is actually not a good fit for some of these settings, especially the really interactive settings that require a lot of expertise. In RLHF, you would take a sample like this, and you would train a reward model, and the reward model is trained by giving humans paired responses and asking which one is better. And humans, in simple case, can say, oh, this response is better than this other one. But if it's a task that requires a lot of expertise, like being a really good tech support agent, the human providing the preferences might not even know what makes a better tech support response. That requires a lot of expertise. In fact, if you want a superhuman agent, you can't rely on human preferences because humans are, by definition, not superhuman. So the problem is, why would humans be better at expressing preferences than at doing the task? Well, they probably wouldn't be. So the goal in dialogue is not to say a particular thing, but to achieve a particular outcome. And for that, we need to go beyond RLHF. So here's an example task that we can use as a benchmark. This is not as interesting as tech support, but it's the one that we're going to use in our evaluation. This is the visual dialogue task proposed by Das et al. In a paper called Learning Cooperative Visual Dialogue Agents with Deep Reinforcement Learning. Here, the questioner, which is the LLM bot, asks questions about a photograph that the answer is looking at. And at the end, they have to guess which photograph it is. So they'll ask like, oh, are there any people? Are they facing each other? And at the end, if they gather the right information, they can guess the right image. So you can turn this into an MDP, or actually a PUMDP, a partially observed Markov decision process. If you say that everything that the other agent says is an observation, everything that you say is an action, and that makes this a sequential process. So the action is what the bot says, the observation is what the human says, the state is the history of observations, and the reward is a dialogue outcome, which is assigned at the very end. So this is not the same as RLHF. RLHF is about learning from human preferences. This is about learning from the dialogue outcome, figuring out what to say now to get the right information later so that you get the outcome you want, so that you can guess the picture at the end. In RLHF, an episode is a single utterance. There is no interaction with an environment. In this setting, an episode is an entire dialogue where you only control what you say. You don't control what the other person says, so the other person is part of the environment. Okay, so can we train on such data with offline RL? Well, what we can actually do is we can adapt the same Q-learning framework, and the way that we can do it is as follows. Let's pretend that we're going to train our language model transformer, and our language model transformer is not going to output probabilities of tokens, but it's actually going to output the Q values of tokens. So let's say that we're at this at the token for the word facing it. In reality, tokens are not words, but I'm going to just pretend like tokens are words so that it's a little easier to illustrate. So here is my tokenization. I realize these are not real tokens, but this is just for the example. So the next token is facing. That's in your response. You're going to train your transformer value function so that it assigns Q values to all the available next tokens. Facing, that's the one in the data set. So that's the one you're going to train. And your loss function is going to minimize the difference between the left-hand side and right-hand side of the Q function, which means that it's going to look at all the available tokens at the next time step and take the max over their Q values, add the reward, and that's your target. Now, the reward is going to be 0, except for at the very end of the conversation, where the reward will be based on the conversation outcome, whether you succeeded or failed. So the interesting thing here is that the training process is not that different from standard maximum likelihood training. In maximum likelihood training, you maximize the probabilities. Here, you instead pull the Q values towards the target values, but it's just a different loss function. So in a language model, you're modeling the probability of the next word given the previous words, or the next token really given the previous tokens. With the value function, you're modeling the probability of succeeding at the task given the previous tokens and the new token that you're about to select. So it's a different probability and it's trained in a different way, but really it's just a number associated with every token, just like before. So the state is all the previous tokens, the action is the new token that you're selecting, and the probability of success is your Q value. So it's basically offline RL, Q learning applied to language models with a Q value for every token. We can evaluate this. This is a system called ILQL. It's a method based on this principle using the IQL algorithm, because you still need to take care of all the offline RL issues. And here we're evaluating it on this visual dialogue task. The questioner is the bot. The answer is a simulated human. It's actually not a real human in this case. It's actually another bot, but it's like a baseline bot that's just simulating the human. And here, for the standard reward function, which is to guess the right answer, the bot learns to ask, fairly targeted questions. You can also change the reward. You can, for example, give the bot a penalty for asking questions that lead to yes or no answers. So it's kind of a toy exercise, but we're trying to see, can we manipulate the answer a little bit? So if you punish the bot for asking questions that lead to yes or no answers, then you get fewer yes or no answers. You get more interesting and informative answers. And this is interesting because the bot is learning to manipulate the answer. It's not rewarded for saying yes or no itself. It's rewarded for not getting somebody else to say yes or no. And you can have an even more conservative penalty that also punishes uninformative answers, and you get quantitative answers. So you can do a lot of interesting stuff with the same exact data, but with different rewards, and elicit different kinds of responses. Now, interestingly enough, we can actually apply very similar ideas to get better dialogues even without good data sets. So let's say that we want, for example, an LLM bot that'll be a very interactive teacher. Here, the teacher is trying to teach machine learning concepts. So the human says, can you teach me about behavior cloning? And the bot asks, well, to start, have you ever come across the term artificial intelligence? And the human says, yes, I've heard those terms, but I don't know what they mean. So the bot can use that to adjust its lesson. Now, if we had lots of data of these kinds of interactive tutoring sessions, then we could use the methods I described before to get a bot that solves this task. But what if we don't have that data? Well, one of the cool things about language models is that they are already modeling human behavior. So we can actually use language models to try to solve this task in zero shot without data. Now, unfortunately, if you just ask, for example, ChatGPT to solve this task in zero shot, that doesn't quite work. So if you ask ChatGPT the same prompt, can you teach me about behavior cloning? It kind of gives you this wall of text because it's not trained to do interactive goal-directed conversations. So it gives you a big questionnaire, and then you have to deal with that somehow. This is not what you want from a very interactive teacher. but the knowledge is in there. These language models understand how humans behave. They just don't know how to hold a conversation. So what you can do instead is you can actually prompt a language model to produce data simulating this kind of dialogue and then use that data with offline RL. So we're going to prompt a synthetic data generator, essentially a kind of a human simulator, to generate dialogues. And these dialogues might not be very good, meaning that the teacher is not necessarily being a very smart teacher, but they are realistic in the sense that they match the distribution of human behaviors, just not necessarily good human behaviors. So this data doesn't have to be good, it just has to be plausible. And language models are very good at generating that. So that gives us a huge data set of interactions, simulated interactions between teachers and students, tutors and students, including very low quality tutors. And then we use this data set with offline RL. And now that RL agent is going to use this data set, analyze it, and figure out what kinds of behaviors lead to successful teaching. And that will get us a better teaching agent. So the idea here is that RL with LLMs is great for tasks that are easy for LLMs to simulate, but hard for them to perform optimally, because you can use the LLM to simulate data. And then with RL, instead of emulating humans, LLMs can now learn to achieve desired outcomes using their understanding of how humans behave. So here's an example dialogue from, in this case, ChatGPT, trying to help a human learn about behavior cloning. You can see that there are very long, very wordy responses. And here's the same task, but with an agent that was trained with this technique. And this is a much smaller language model, but it was trained with RL on LLM-generated data. And you can see the responses are much shorter and much more goal-directed. In fact, it says like, I've heard those terms, but I'm not exactly sure what they mean. The agent says, no problem at all. Let's take it step by step. Have you ever used a computer or smartphone? So it asks these very targeted questions to understand the knowledge level of the student so that it can teach them more optimally. Okay, so in this talk, I talked about what we can accomplish if we combine data and optimization. I talked about fundamentals of offline RL, how it can be used with foundation models for robotics, with generative models, and with language models. And I think that underlying all this is a kind of an interesting perspective on the bitter lesson. Many of you might have read Richard Sutton's essay about the bitter lesson, where he says that we have to learn the bitter lesson that building in how we think does not work in the long run. And the two methods that seem to scale arbitrarily are learning and search. A lot of people misunderstand this essay to think that, well, what it means is that we just have to like take lots of GPUs and do lots of supervised learning with larger and larger language models. But that's not what the essay is actually saying. It's saying that you need learning and search. What is learning? Well, we know what learning is. It's using data to extract patterns. What is search? Well, search is using computation to extract inferences. Search is optimization. Search is essentially RL. So we need both of them. We need both learning and search. We need to extract patterns, and we need some optimization process that uses typically iterative computation to make rational decisions. Learning allows us to understand the world. Search leverages that understanding to achieve emergent behaviors. Data without optimization doesn't allow us to solve new problems in new ways. Optimization without data is hard to apply to the real world outside of simulators. Thank you very much for listening, and I'd be happy to take questions.
Thank you, Sergey. That was extremely informative and yet very lucid talk. I believe all the participants have been benefited from this. So now we open up the session for question answer. Dear participants, if you have your questions, you can unmute yourself and ask or type in the chat box, please.
Yes, actually, I have a few questions. Not questions technically, but I want to share some thoughts of mine, some curiosities I want to confirm. Yeah, so thanks again, Sergey. And this talk was simply phenomenal. And I mean, great would be an understatement. The organization, the humorous tidbits you put in the middle of those slides, I found it very amusing, very interesting. Thanks for such a great talk. So I once read your paper, Datasets for Deep Data-Driven RL, D4RL, and I also attempted to work with such kind of datasets. And what I found from my personal experience is that datasets for offline RL are pretty huge. So what's your take on the sample complexity perspective? This is the first question.
Yeah, and thank you very much for your kind words. That means a lot to me. Yeah, so how can I answer this question? So I think that it depends on what we want to accomplish. I think that large data sets are a really big problem if you need high quality data. So if you really need high quality data for your particular task, then it's a big challenge if you have high sample complexity. But well, and in fact, we can try to develop methods that work better in those regimes. But I think that one of the big promises of offline RL methods is that they can use large amounts of lower quality data. Because unlike, for example, direct imitation learning techniques, offline RL methods don't require the data to be examples of optimal behavior. So
Yes.
perhaps because the requirement is lower, it might be more practical to obtain large data sets for offline RL than for standard supervised learning techniques. That said, of course, you're right that RL methods, deep RL methods in general tend to require large data sets. So it is a big challenge. And I think it has to do with the particular constraints of your domain.
Yes. So my second question is mainly from a performance and safety point of view. So for robotic tasks, we all know that safety is a really important aspect that's worth consideration. So now you just mentioned that we try to develop foundational models for robotics that trying to develop a single policy for a wide set of tasks. So now thinking about the combination of distributional shift and safety, so how to deal with these two issues together?
Yeah, that's a really good question. I mean, in general, this is a huge challenge with anything involving robotic learning. I do think that some ideas, so offline RL by itself is not a solution to safety. So offline RL methods do need to address the distributional shift problem, but it's really addressed from the standpoint of avoiding action distribution shift. It doesn't necessarily by itself avoid going into dangerous regions, but many of the ideas from offline RL, these conservatism or pessimism ideas, can be extended to provide essentially pessimism
Right.
against epistemic uncertainty. And there are papers that have explored this perspective. Several students in my group have studied this. There's a paper by my student Katie Kang called Lyapunov density models that actually takes a kind of control theoretic perspective on the problem and combines ideas from conservative Q learning with some ideas from controls to basically train kind of safety constraints. I think there's a lot of work left to be done there. The problem is by no means solved, and there's some huge challenges, but it may be that some of the ideas in offline RL can give us some tools to get started on that.
Oh, that's awesome. And in the light of this question, so could we have, some prior distributions or some priors in any forms from which we can sample potential actions? And if so, how to leverage such prior models, while running pre-trained models, and then after that running the RL setup or fine-tuning using online RL?
Yeah,
So
great
what's the role
question.
of
So
prior here?
I think that's a really good question. I think it's entirely possible. So it depends a little bit on what you want during the online RL phase. So if you want the online RL phase to sort of explore beyond the data, then it's very difficult to handle safety because obviously if you're going beyond, then you're going to encounter new things. But one thing you could do is you could actually use offline data to train a collection of primitives, and that can be done in a variety of ways, essentially latent variable models. And then when you're performing online RL, only allow online RL to use those primitives as the action space. And that will prevent the online RL process from selecting actions that are too different from what was seen in the offline data. Now, it's a trade-off because when you do that, it's easier to remain safe, but it's also harder to find new things beyond what you saw in the offline data. So there's a trade-off.
Yes. Thanks for the great answer. And my last question is this. When speaking about LLMs with dialogue machines and all, so I think sometimes it's really difficult, it's really challenging to ensure that the human simulations, I mean, whenever we are talking about dialogues, we humans are the environments, right? RLHF, RLAIF, such sort of things. So I think it's a big challenge to ensure that these simulations are actually aligned with realistic real world human behavior. So my big question is this: are we sort of trying to find out the because RL could be thought of as a counterfactual reasoning thing. So, for example, what if I took action A from a particular state S? If I had taken A prime, a completely different action, what would have been the outcome? So now, are we trying to deal with hidden states here?
Yeah, I think that's exactly right. That there's a lot of there's a lot of hidden state in human interaction, and I don't think that so far I haven't these kinds of methods that perform RL with language models, they mostly don't do anything particularly special about that. They kind of just rely on the context of the conversation being sufficient to implicitly infer the hidden state. But I don't know if that's enough, because there's a lot of hidden state, a lot of context that is not present in the conversation that affects how humans will respond, and that's a big challenge. So I think that's an open problem for the future.
Okay. Thanks, Sergey. Again, thank you so much.
So I think there are
it's-
a few questions in the chat also, Sergey, if you can look
Sure,
into
yeah, I
them.
could take those. Using the RTX manipulation model, will it be generalizable to a new type of gripper? And will it be difficult to generate data with a new type of gripper? Okay, so one clarification about RTX, this was the multi-robot project. We actually, the evaluations use the same robots that are seen in the data. So the test is not whether it generalizes to new robots. It's actually for now only improving the performance of the seen robots. Now, generalization to new robots is much harder. So with the current iteration of RTX, it does not generalize effectively to new robots yet. It can be fine-tuned to new robots. So there's actually a new paper called Octo from my lab at UC Berkeley that trains on the RTX dataset and then fine-tunes to new robots. But zero-shot generalization is still a challenge. Now, I do suspect that zero-shot generalization will be possible in the future when the multi-robot dataset is diverse enough. But at this stage, the only thing we've been able to achieve is few-shot fine-tuning. The other part of your question, are we able to learn multi-step actions or systems that need high-level planner as part of the solution? Yeah, that's a very good question. There has, in fact, been work on hierarchical offline RL, basically offline RL methods that have a high-level policy and a low-level policy. And these methods do aim to tackle more or less precisely this challenge. There are even methods that have model-based higher levels and model-free lower levels. So it's an active area of research. It is challenging to get that right, and as the horizon gets long enough, eventually it becomes hard. But it's something that people are working on. Last question there is, how can we obtain superhuman behaviors from our agents if we are training it on human interactions? So the idea there is the following, that any single human interaction might be suboptimal in some way. But if you can analyze lots of interactions and essentially do as well as the best human in each situation, then overall you'll be better than the best human, because maybe one human is really good at a particular part of, maybe one person is very good at the technical side of tech support, and another human is really good at the social side, basically getting the customer to be patient. So if you get a bot that is the best of both of those, then it'll be better than any one human. So that's basically the principle.
So any other question from any other participant, please?
Yes, I have a question actually. One more question again. I apologize if I'm asking too many questions.
No, it's fine. Just go on.
So Sergey, what's your take on causality and its related effects on offline RL and also bisimulation? Because I have read some very interesting papers regarding bisimulation and the combination of offline RL.
Yeah, great question. So as you pointed out in your previous question, the problem of selecting actions in offline RL is a kind of counterfactual problem. You're essentially saying, if I had taken a different action than I actually did in the data set, will that be better or worse? And in its most general form, that is basically a problem that implicates causality. It's a counterfactual question. So if you want to answer any counterfactual question, then you need to have a causal model. The key idea with offline RL is that you don't have to answer every question. You don't have to know how good every single action is. You just need to find some action that is better. So it's okay to say that for this action, I don't know how good it is, so I will stay safe and avoid taking it. So the offline RL problem is very related to causal inference, but it's in some ways easier because you don't actually need a true causal model. You can simply avoid some of the questions.
And about bisimulation?
Yeah, so that's a good question. I think bisimulation as a representation learning approach can be combined with offline RL methods, and that's something that people have done before. I don't know if bisimulation itself if there's any more depth to it than that, other than that it's a representation learning technique that could be combined. But yeah, it's a very useful representation learning technique.
Thank you. Thanks for the great answers. Thank you. Thank you again.
Thank you for your questions.
Okay, so if participants don't have any further question, Let us extend a heartfelt thank you to Dr. Sergey Levine for his outstanding presentation and his deep insights into the RL for generation, large language models, and related topics have truly broadened the understanding of this complex field for our participants, I hope. So on behalf of all attendees, I express my gratitude for Sergey's invaluable contribution to our winter school this year. And let us hope he would be available for future events also at Indian Statistical Institute. At some point of time, Sergey, if you plan to visit India, we would be very happy to host you in this very old and pioneering institute called Indian Statistical Institute, which is which pioneered the study of statistics in all over Asia long back in 1940s. Okay. And if you are familiar with the Mahalanobis distance function, the d-square function, which is very well used in machine learning. So the founder of our institute, Dr. P.C. Mahalanobis, was the proposer or inventor of that distance function. So we would be very happy to host you physically at some point of time in future. Thank you very much once again.
Wonderful. Thank you so much for the invitation, and thank you all for listening.
Thank you.